It's pretty incredible when you think about it. Every single thing we do online, it just works. But have you ever really considered why? Well, today we're pulling back the curtain on the transport layer. This is the unsung hero, the meticulous courier service that makes sure everything you do online actually gets where it's going. It all starts with something so simple. Something you do 100 times a day without a second thought. You see a link, you click it, and boom, the page just appears. It feels totally instant, right? But what's really happening in that split second is anything but simple. That one click sends a request out into the wild, chaotic jungle of the internet. So how on earth does a complete, perfect web page find its way through all that noise and back to your screen every single time? All right, so let's break this down. Before anything can be sent to you, your computer has to ask for it first. And that first step, that's the job of what we call the application layer. You can think of this part as basically filling out a shipping label for a package. Your web browser creates a very specific message, an HTTP GET request, which is just a fancy way of saying, hey, server over there, can you please send me all the files for this web page? That request, that's our precious cargo. Okay, so here's the fundamental problem we're up against. The internet itself, the actual network of wires and routers that connects everything, it's completely unreliable. Seriously, it's not some perfectly paved superhighway. It's more like the Wild West or a really stormy sea. And out on this stormy sea, a few things can go horribly wrong with our data, which, by the way, gets broken up into these tiny pieces called packets. First, a packet can just get lost. Poof, gone forever into the digital void. Second, they can show up all jumbled and completely out of order. And third, they can get corrupted along the way, with the data getting scrambled by errors. And that right there is the multi-trillion-dollar question, isn't it? If the network itself is just a chaotic mess, how in the world do we get reliable things like email or file downloads, or even just a simple web page to load correctly? How do you build something dependable on top of something that is fundamentally undependable? Well, the answer is an amazing set of rules, a protocol that lives in the transport layer, and its name is TCP. This is the system that steps in to tame all that chaos. And this is the whole point of it. TCP, or Transmission Control Protocol, was built from the ground up to solve this exact problem. It acts like the world's most detail-oriented courier. It takes on the full responsibility of making sure every single piece of your data gets to its destination, perfectly intact, and in the right order. Now, TCP isn't the only game in town. It's got a sibling, UDP, and the difference is pretty simple. If TCP is like sending a certified letter that's tracked, signed for, and guaranteed to arrive, UDP is like throwing a postcard in a mailbox. It's way, way faster, but there are no guarantees. You just kind of hope it gets there. For a web page, you absolutely need the guarantee, but for a live video call, sometimes you're willing to trade a little bit of reliability for speed. So how does TCP actually pull this off? Well, its first trick is something called the Internet Checksum. Before TCP sends a packet, it basically does a quick math problem on all the data inside and attaches the answer. When the packet arrives, the receiver does the exact same math. If the answers don't match up, it knows the data got corrupted and it just throws that packet away. It's like a brilliant automatic proofreader. Okay, next up, to fix that out-of-order problem, TCP acts like a bookbinder. It takes a big file, like our webpage, breaks it into smaller chunks called segments, and then it gives every single one a unique page number. We call it a sequence number. And just like that, the receiver knows exactly how to put the puzzle back together in the correct order. And here's where it gets really clever. TCP has this constant feedback loop. It doesn't just send data and hope for the best. After the receiver gets a piece, let's say the one starting at byte 61, it sends a little message back called an acknowledgement, or ACK. But here's the genius part. It doesn't just say, hey, I got 61. It says, okay, I got everything up to 840. So I'm now expecting the piece that starts with 841. It's a 2-for-1 message. It confirms what it got and tells the sender what to send next. So efficient. Okay, but what about the biggest problem of all? What happens when one of those packets just vanishes? Well, this is where that whole sequence number and ACK system becomes truly elegant. So let's walk through this scenario. The sender sends out packets 1, 2, and 3. But, oh no, packet number 2 gets lost somewhere on the internet. A little while later, the receiver gets packet 3. But it looks at its checklist and goes, wait a minute, I have packet 1 and packet 3, but where's packet 2? So what does it do? It sends another AK back to the sender, but it's a duplicate. It once again asks for packet 841. It's this really polite but firm way of saying, hey, I'm still missing this piece over here. You need to send it again. So TCP can handle lost packets, it can handle errors. It's amazing. But there's an even bigger problem it has to solve. What if a sender starts sending data so fast that it completely overwhelms the network, creating a massive traffic jam for everyone online? This is where TCP proves it's a good internet citizen. It has this incredible built-in system called congestion control. It's constantly feeling out the network, trying to figure out how much traffic it can handle right now, and then adjusting its own sending speed so it doesn't cause gridlock. It always starts with a phase called slow start. It doesn't just blast data out at full speed. Instead, it sends just one little segment. When it gets the thumbs up, that ACK, it sends 2, then 4, then 8. It's growing its sending speed exponentially, really quickly probing to see where the network speed limit is. But once it gets close to what it thinks that limit is, it switches gears into congestion avoidance. Now, instead of doubling its speed, it slows way down, adding just one segment's worth of data each time. It's a much more careful, gradual increase, trying to use every last bit of available bandwidth without tipping over the edge. So what happens when it sees warning signs? Well, if the sender gets 3 of those duplicate ACKs in a row, the ones that say, hey, I'm still waiting, it takes that as a huge clue. It assumes a packet was lost, probably because some router on the network is getting overwhelmed. And its reaction is instant. It cuts its sending speed in half to give the network some room to breathe. And then there's the emergency brake. If an ACK just doesn't come back at all after a certain amount of time, a timeout, TCP assumes the worst. It figures there must be a major traffic jam out there, so it slams on the brakes, drops its sending rate all the way back down to just one segment, and starts the whole slow start process over again. This single mechanism is one of the key things preventing the entire internet from collapsing on itself every day. So as we start to put it all together, you can see that what's really happening in the transport layer is this constant balancing act, this fundamental trade-off that's being managed for us behind the scenes. When you look at the big picture, the transport layer's whole job is to manage this trade-off between speed and reliability. TCP gives us that rock-solid, guaranteed delivery we need for things like web pages and file transfers, using all those amazing tools we talked about. And its sibling, UDP, gives us that raw, best-effort speed we want for gaming or streaming. Without this hidden layer making millions of these tiny decisions for us every second, the internet as we know it, well, it just wouldn't work. So here's something to think about. The next time you're on a video call and it stutters for a second or your online game lags, what's really happening? Are you just seeing the price you pay for choosing UDP's raw speed over TCP's certainty? Or are you actually feeling the ghost of TCP's congestion controls somewhere out on the internet, hitting the brakes just enough to keep the whole system from grinding to a halt? Something to ponder, right?